All right, hi everyone. Thanks so much for coming early this morning for our, I guess, second iteration of the agent-based models in neuroscience workshop. This is done together with my co-organizers, Elliot Abe and Satpreet Singh, who's online. And Sat will have a few words at the end, since he started this workshop actually last year, and I was grateful to be one of the invited speakers. So today, I'm just going to spend the first maybe 10 minutes just giving a high level, maybe not only an overview, but also a motivation for why this is not a terrible idea and maybe a timely one, especially given kind of the confluence of both AI and neuroscience that we're seeing today, both with advances in neurotechnology, but also advances in artificial intelligence. So maybe there's two kind of broad motivations to begin with of why we want to have agent-based models, or maybe another word for them that we have in our lexicon now is neuroagents. One is kind of an obvious one, maybe from just observing behavior. The brains aren't in a vat; they produce adaptive goal-directed behavior. So, for example, you see this you see this person hitting this tennis ball. And he's anticipating the motion of the ball before he hits it. So he has some kind of model of the world of how the ball will move and anticipates and adjusts his actions accordingly. Animals do this too. So here you see a squirrel going for food, but on its initial attempt, it fails because of the slinky's material properties. But it's smart and it observes the oscillations of the slinky, and then rapidly climbs up when it's ready. So this is something that's really common and shared between us and animals. The second aspect of it, which is really more of I think a timely neuroscience motivation, is we're now getting access to whole brain data rather than individual brain areas in isolation. And so this is providing unique access to cognition while an animal is awake and behaving. So this is from the IBL, for example, with rodents and neuropixels that are being displayed here. But of course, it's not even limited to rodents. There's, for example, the very famous recent flywire connectome of the Drosophila and corresponding whole brain recording in certain circumstances there. Work, for example, from Misha Aren's group at Genelia has done, for example, whole brain optical imaging of zebrafish while they're in a futility-induced passive state, and can image not only neurons but radial astrocytes. With all this data comes this kind of responsibility of how are we going to go and make sense of it. And maybe the argument that we'll pose here is that neuroagents are providing a way to reverse engineer the animal brain. And from an AI point of view, so that's the neuro motivation. But from an AI point of view, the motivation is as follows: is that current AI, which is kind of trained passively to produce very photorealistic generated video outputs, struggles to kind of understand the physical world. So here's an example from OpenAI's Sora that came out a couple years ago, where you see this kind of chair pop out of nowhere. So there's a lack of object permanence. And on top of that, the way in which the chair interacts with folks, it's kind of in outer space. It's very aphysical, right? So it's highly photorealistic, but it's highly aphysical. And so maybe one argument from an intelligence point of view, more broadly speaking, is that maybe what's missing is this kind of more core thing of not just passively observing the world, but actually interacting with it and being embodied in it and updating and having feedback from that. And you might ask, why might we want to reverse engineer natural intelligence, of all these kinds of species that we see here, including even the capabilities of babies, is that currently, as it stands, and this is rapidly changing, of course, is that animals and humans perform behaviors that we've yet to successfully engineer in AI agents today. So I've listed a few: prediction and planning requiring world models and memory, building, video world models, for example, that are physically realistic is one challenge I just mentioned earlier. Adaptive online motor control, which not only involves embodiment, but also autonomy and lifelong learning. And so the test time reasoning paradigm that we see today is really just one small snippet of that, where you're not updating the weights, but you still need to do that without forgetting everything. And I think that's still a core challenge that we have today. And so what we kind of think of it is that the specific capabilities of humans and animals become our concrete engineering targets. And maybe the scientific question of kind of using neuroagents to reverse engineer whole brain data is to address this notion of how does the sensory motor loop work? How does the brain represent, predict, plan, and enable action? And so, oh, here, sorry, let me hide, yeah. Okay. And so we can kind of think of this maybe in a modularized way, where you have a perception module, a world model, a future inference module. You plan within the future trajectories you've produced, and then you execute those actions in an embodiment. And we have several choices here, ranging from rodents to flies to zebrafish. And then what you can think of is, also having intrinsic goals that aren't externally defined but are internally generated that guide this entire process. And finally, that each of these modules might themselves be hypotheses for individual brain areas, and then how these arrows are a hypothesis for the interaction between these brain areas. So here I've just highlighted a rodent brain with the, say, color-coded hypothesized corresponding regions. But again, we're not limited to one species, and in fact, it gives us a range of practical outcomes. For example, not only open source benchmarks, but it can predict outcomes for new experiments in silico much more cheaply if you had an in silico whole brain than a biological one that's of high fidelity. From a science point of view, it provides a systems level understanding of an organism. And these things deal with looking at the intrinsic goals, which you can only really look at with an agent, identifying biological learning rules, how you update the agent after you've gotten it, as well as looking at species conserved algorithms across these modules. So what I mean by that is that this sensory motor loop is shared across species. And so you could look at homolog areas across different species and make comparisons of what learning rules and tasks and architectures reside in each of these modules that are shared or similar and different across species. So we have a range of questions that we're going to talk about in the panel today, ranging from theory, how can current models in theoretical neuroscience be extended to the agentic setting? How does the body or interoception and intrinsic motivation contribute to behavior? Are there cross-species principles? Are there behaviors that can only be explained by going beyond basic RL algorithms? And what level of realism is needed, both to formulate and test new hypotheses, but also to identify neural mechanisms about complex behaviors and use this as a platform. We can correspondingly ask, what experiments might be best to better run in a neuroagent than, say, in the biological wetware? And can we move beyond the assumption of adult agents and start studying in a more formal way development and plasticity and compare those to trajectories in real animals? And how can we, say, model social behaviors as well and multi-agent settings? And then finally, I think maybe from a tech point of view is, given that we have multiple models, body models, rodent, flies, zebrafish, and more abstract ones available, how do you pick one for your project? And when do you decide to build your own or to use and leverage what's already out there in the community? Should you have muscles in your body, for example? And where are we going? What new software tools are available and hardware developments that enable new and what kinds of fundamental questions? So today we have a great range of speakers, from theory to experiments to computational modeling, some of whom will be virtual, but mostly in person, and we'll have a panel discussion as well. And so the format will be 20-minute talks plus a 5-minute Q&A and one 30-minute panel in both the morning and afternoon session. So we'll have a morning session today. This is the schedule, and we'll break for we'll have the panel at noon, and we'll break for lunch until 3 p.m. And we'll have a coffee break at 10:30, and then we'll have a similar setup in the afternoon where we'll have a number of great speakers, and then have a panel discussion at 5:20, and then having closing remarks ending at 6. Okay. Yeah, that's it. Sat, do you have a few words?
Yeah, so I just wanted to say hello to everybody over there. Sorry that I could not make it in person this year, but I'm very excited about our lineup today. The panel discussions are a great place to discuss not just what is happening right now, but what should be happening next. So I encourage everybody to please note your questions and bring them to the panels. We're hoping to have a very interactive and forward-looking discussion. looking forward to a great day. I hope you enjoy the workshop.
Thank you. Okay. And